Hello, MEGN 300. This is Dr. Wheeler, and today we are talking about signals and the waveform data type in LabVIEW. So what we'll be talking about in this video is, first of all, what is a signal? What are we talking about when we talk about signals in an instrumentation context? How do we represent physical variables in a way that's meaningful and useful inside of a computer? And then how specifically does LabVIEW represent signals inside of the LabVIEW programming environment? So that's what's on the agenda for today. So let's go ahead and jump in to a few slides here. All right. So first of all, we need to talk about what a signal is. So signal is the desired information that flows through an instrument. So recall an instrument is a device that converts this measured variable that's out in space into some sort of useful output that we can use as an engineer to interpret information about the measured variable, or maybe feed that into a computer that can control the measured variable somehow. A signal can be any sort of information. It can be optical, it can be mechanical, like displacement, or it could be any other physical variable. So here's a few examples of that. So we have optical types of signals. So in laser diagnostics, if you're trying to measure quantities with light, oftentimes the signal is optical. It's a laser beam that you're trying to capture and measure somehow. You can have displacement inside of a mercury thermometer as you watch the mercury go up and down the scale. That's a physical displacement. Or you could have a rotary displacement on like a pressure gauge. So as the needle moves back and forth, you can consider that displacement to be a signal also. One of the most common types of signals that you'll run into are voltage signals. Voltages are really nice for us to work with. We have lots of electronics that are good at reading voltages, and we can interpret those very easily. So a lot of times you'll see instruments that are designed to convert some sort of physical phenomenon into a voltage that we can then measure. And that's primarily what we'll be focused on in this class. All right. So first of all, we should talk about different types of voltage signals that we can run into. So there's two broad categories here. So there's analog voltage signals and there's digital voltage signals. So digital voltage signals you might be familiar with from things like USB ports or any sort of equipment that's working with a computer. Typically, what you have happening inside of those cables is there's a voltage that alternates between a high and a low state to represent 0 and 1, and it flicks back and forth in time to send information that way. What we deal with more in this class are the analog voltage signals. So analog signals can have a value other than just on or off. They can have a whole continuous range of values that can be represented with an analog voltage signal. All right, so that's primarily what we'll be looking at. Most of the types of instruments that we use produce an analog output. So in these analog signals, the voltage is varying as a function of time. And when we have a true analog signal, we have effectively an infinite number of data points. Now, that's really nice because we can have as much resolution as we want out of an analog signal most of the time, but we can't actually work with an infinite number of data points in a computer, right? So we want to capture that information in LabVIEW and process that data somehow, and we can't store an infinite number of data points in memory. We just don't have enough memory to do that. So what we need to do is convert this analog signal into something that is useful and can be stored in a computer. And the way we go about doing that is with a DAC. All right, so DAC is short for data acquisition. It's just a general term of any sort of device that's collecting an analog voltage signal and turning it into something that's useful in the computer and acquiring that data. So what it does is it's going to read the analog voltage and represent it as numbers that can be stored in a digital format. So the central component in a DAC is called the ADC, or sometimes analog to digital converter is the full name. And what it does is just what the name says. It takes an analog signal, converts it into numbers so that those can be stored in the computer. All right. So in our lab, we have DACs from National Instruments. So we typically refer to those as just the DAC. But keep in mind, it's a general term. It can refer to a variety of different specific devices, not just the one that we use here in this lab. All right. So the way the DAC converts the analog signal to a digital representation is it samples the analog signal. So what it's going to do is it's periodically going to come and it will take a measurement of the voltage, and then it waits a certain amount of time, and then it comes back and it takes another voltage reading, and it stores basically a big list of numbers. So your continuously varying signal is now a series of discrete points. Instead of having an infinite number of data points, you have a list of a fixed finite number of data points after the DAC has sampled your analog signal. So in just broad terms, here's what this kind of looks like. Is we have our analog signal on the left over here. It's smoothly varying. We have an infinite number of data points. We feed that into the DAC, and what it spits out is a discrete XY plot. So you think of each data point has an X value and a Y value, and there's no longer an infinite number of those data points. There's a fixed number of those that's finite. We call that our digital representation of the signal. All right, so let's talk about how the DAC actually goes about doing this conversion. So the DAC is taking readings at a predetermined time, right? And there's a specific amount of time that passes between each of the data points that are collected. We call that DT. It's given in units of seconds. Sometimes you'll throw the prefix on there. Milliseconds is pretty common for most applications. If we have a really fast phenomenon that we need to capture, you might have to get a high-speed DAC that would be capable of measuring DT in terms of microseconds or maybe even picoseconds. And that's the time that passes from one data point to the next data point when it's collected, right? We could also talk about how quickly we're collecting data in terms of the sample rate, which is usually given the variable S, big S, and that is going to be given in units of hertz, right? So the relationship between the sample rate and DT is that the sample rate is just 1 over DT, right? They're just the inverse of each other. So, for example, if we configure our DAC, so we're reading a voltage 10 times a second, we would say that DT is 0.1 seconds, right? So it would be 0.1 seconds that pass between each data point if we have 10 of them in 1 second. And the sample rate, since we're taking 10 samples a second, is going to be 10 hertz, right? And you can see that those numbers are just the inverse of one another also. So you can convert back and forth between sample rate and DT using that formula. All right, so that was the x-axis of how we determine where all the data points are in the x-axis. We need to talk about how do we figure out where those data points are in the y-axis. So the analog to digital converter on the DAC has a limited number of bits. So a bit can be either 0 or 1 that it uses to represent voltage values. So effectively, it takes these bits and it makes numbers that represent how much voltage you have present at the channel, and that's how the sample gets converted into a number. Our DAC has an analog to digital converter with 16 bits, so it can represent 2 to the 16 unique numbers or voltage values. Okay, and the A to D has a range of voltage values that it can detect as well. So you can't just put extremely high voltages into the DAC. That'll destroy the DAC. It's calibrated to work with a certain range of voltages. By default, the DAC's device will go from negative 10 volts to positive 10 volts, so it has a 20 volt range. Right? There's a possibility of 20 different volts that could go into the analog to digital converter. And you can adjust that also. So there's some settings that you can change in the DAC to make that range smaller if you needed it for your application. But let's talk about how that affects the quantization of on the y-axis. All right, so the number of bits that you have on your analog to digital converter and the range of the ADC will determine the resolution. Right, so the resolution is how small of a voltage change we can detect with the DAC device, right? So let's do an example of this here. So if we have an Arduino Uno, its analog to digital converter has 10 bits, and it has a range from 0 to 5 volts. We want to know what's the smallest change in voltage that the Uno can detect, right? So first of all, we need to know the range. So how many volts does this need to cover? So there's a since we go from 5 to 0 volts, there's 5 volts of range that we're covering with the analog to digital converter that we have to represent as unique numbers. And then we have to see, well, how many unique numbers do we have to represent the volts in that range? And since we have 10 bits, we have 2 to the 10 unique numbers that we can represent with those bits. So that's 1024 different unique values that we can represent. So the resolution is going to be our range divided by the total number of unique numbers that we can represent with the bits on the analog to digital converter. So 1024 in this case. And if we do that math and round a little bit, it comes out to 0.005 volts per count. So that's the smallest change in voltage that we can see with the analog to digital converter on a Arduino Uno. Now, the DAC cards in the lab are a little bit fancier than Arduino Uno, so we have those 16 bits. So one of your questions on your assignment is to figure out what's the smallest change in voltage that you can see with the DAC card in the lab, and it's quite a bit smaller than what you can see with the Uno. All right, so let's talk about how LabVIEW takes this information and then interprets it and stores it inside of the LabVIEW programming environment. Okay, so in general, what we have after we've gone through data acquisition and analog to digital conversion is we have basically a big list of voltage values in the computer. So the voltage values are the y-axis, and then each voltage value has a time value or a timestamp associated with it to fix its location on the x-axis. So time becomes our x location, and voltage becomes our y location. That's how we locate where each data point is on a graph. So the way LabVIEW goes about doing this is it has a special data type that's specifically for this task because it's so common to be working with this kind of data in LabVIEW. And this data type is called the waveform. So waveform is essentially a cluster, so like a data structure that has 3 components inside of it. It has an array of y values, so that's your list of your voltage values. It has a start time of when you started collecting data, and it has dt, right? So dt is, again, the time between each sample. So they could have stored a big 2D array that had a list of y values and a list of x values. What they're doing with the waveform data type is instead of having to store each x value individually, each time value individually, what they're saying is, well, typically when people are doing data acquisition, the dt is a fixed time that doesn't change as you're collecting data. So rather than storing each data point and using all the computer's memory to store time values that are predictable, you just store 2 numbers. You store a start time and dt, and then you can calculate what all of the individual timestamps for each data point are after the fact, just using those 2 numbers. So you can save some computer memory by using a waveform data type rather than using like a 2D array to represent those numbers. All right, so with that, let's jump over to LabVIEW and take a look at what the waveform actually looks like in the LabVIEW programming environment. Okay, so I've jumped over to LabVIEW so we can take a look at how we represent waveform variables and how they work in the LabVIEW programming environment. And what I've done here is I've put together a really simple explanation VI, example VI, so that we can take a look at how the waveform variable works. So what I have here is we have a graph, a waveform graph, so that we can plot what's the data that's stored in our waveform variable. And then the way this works is we have a while loop. So when I hit start, this is going to continuously run. We have a simulate signal block, which is going to generate a waveform variable for us. It actually generates a dynamic data type, and I've converted that into the waveform variable so that we can look at what's in a waveform variable for this exercise. And I have a wait until next millisecond multiple just to control the loop timing so that the loop doesn't run very, very fast. And we should have this run nice and smoothly. When I hit go on this, we should see that sine wave slowly creep across the graph here. So let's go ahead and stop that. All right, so let's look at what's inside of this simulate signal block. The way that you get this block is if you go up here and right click to bring up our menu, we go to express input, And it's going off the screen a little here, but simulate signal is under input, and you can get a block that looks like this, right? And what this will let you do is it lets you generate signals, all right? So we can select different signal types that we would want. If we wanted a square wave, we could generate a square wave instead of a sine. So I just have this set to a sine. The frequency of the sine is 10.1 hertz. We did the 10.1 because that's not an even multiple of the essentially the graph size, so it'll slowly crawl across the graph, and rather than just looking like a static sine wave if we did exactly 10 hertz. We can set the amplitude. You can do things like add noise. And then down here is where this gets a little bit interesting based off of what we've talked about previously. So here we have the samples per second, so that's our sample rate. So how many data points per second our waveform is going to contain. In this case, we're going to have 1,000 data points per second, and we're generating 100 samples. So that means that every time this VI runs and the loop iterates, it's going to generate 0.1 seconds worth of data based off of these settings here. Okay, so that's what should be contained in our waveform data type, which is we should have a Y array of Y values with 100 data points in it. And we should have a start time when this started recording, and then the DT information should also be saved. So let's go ahead and hit OK so we can go back to our VI. And we can see if we come out of here, we convert into the waveform data type, and this sort of brown wire is going to contain our waveform data. So let's take a look at what's inside of this waveform data type. So the waveform itself is actually a special type of cluster. So we've used clusters to bundle variables together before in LabVIEW. The waveform data type is essentially just a special case of a bundle or of a cluster where it holds the array of Y values, the start time, and the DT are the three fixed variables in there. We can retrieve those from the waveform. So if we go back into our block diagram and open up our menu, there's a waveform palette, and we can get waveform components to pull these values out. So if I drop that block down, you can see right now this is going to pull out the array of Y values. I can also expand this out and then select which attributes I want. I have three options: the Y values, the DT, or the T naught, which would be the start time of when we started collecting data. So let's take our waveform and we're going to put it into this block so that we can get those out. And let's create some indicators so that we can see what's inside of these. So we'll add an indicator to the front panel. So we'll be able to see the values that are in that array of Y values. We can add an indicator for our DT so we can see what our DT value is. And let's add an indicator for our T naught so we can see the start time. All right, and we will arrange these a little bit more nicely on the front panel. And there we are. So let's go ahead and run the VI, and we'll see what's inside of that waveform variable. All right, so you can see our Y values over here changing as that scrolls by. So there's actually 100 elements in here. We're obviously not showing all of those because we'd run out of room to show all of them. But you can see as they change, as that sine wave scrolls across the screen, the Y values are changing. The DT is fixed, right? Remember that was set inside of our simulate signals block where we had the samples per second. That's what's fixing that DT. And we have 1,000 seconds, or 1,000 samples per second, so we have 0.001 seconds between each sample. So that's how we get our DT value. And then the time when we started recording is kind of arbitrary. You can see we're not actually recording this video back in 1903, as you might imagine, but it's just a starting place that it uses to calculate the time between each of the samples. Typically, we just use whatever the default value is because we tend not to care so much about the absolute time in the current year when the data was recorded. We just more care about the relative timing between different data points. So you can see that's what's inside of the waveform data type.